So I'm going to talk about energy efficiency. This is very simply the energy you use divided by the energy that was produced. So in a couple examples, you may have using a propane barbecue or a natural gas oven or some sort of heat source to heat up food. And this is one of the examples that we're going to look at that brings in the heat transfer concept. We're going to use standard molar enthalpies of formation, bringing all that together in a multi-step problem. So often you're going to look at the energy used as your system. Okay, this is what is taking in energy. But like a barbecue, you're going to say you're cooking a burger. That burger isn't going to get 100% of the heat that is being produced by the barbecue. Stuff is cooking other food on the barbecue, being lost to the air, just heating up the surroundings. So the burger alone would be the system, and we're going to figure out how much is used there. So in our first example, we're going to look at heating up a chicken thigh on a propane barbecue. So the example reads, if 2.45 grams of propane was used on a barbecue to heat up an 89.1 gram chicken thigh from 4.5 degrees Celsius, so coming out of the fridge, to 81.3 degrees Celsius, a good temperature to heat the chicken to. What is the energy efficiency of the barbecue? You can assume that the specific heat capacity of the chicken thigh is 1.32 joules per gram degree Celsius. So it's a multi-step problem. Let's look at heat transfer first. So in the heat transfer, we're going to look at the chicken. And given in the question, the chicken thigh is 89.1 grams. The specific heat capacity was 1.32 joules per gram degrees Celsius, and our temperature change was from 4.5 to 81.3, giving a final delta T of 76.8 degrees Celsius. We multiply all those values together and you get 9,032.6 joules. Now, using the law of conservation of energy, we're going to say that Q is negative delta H to jump from our system into our surroundings so that we can compare the efficiency. We're going to convert this to kilojoules at the same time and know that our delta H of the energy being used is negative 9.0326 kilojoules. Okay. This is the first part of our energy efficiency problem. It's going to be the energy used, and I'm going to put this in the corner here, 9.0326, and keep that value for the next step. We're now going to look at the propane barbecue, and this is essentially our source. This is what is producing the energy, and the barbecue is going to be the surroundings around the chicken. So we're going to assume complete combustion, which is an assumption you can make for all of these energy efficiency questions, and write out the combustion of propane. C3H8 plus O2, we need 5O2, 3CO2 plus 4H2O. Okay? All of our states for this problem will be gaseous, and this will matter because using this equation, we're going to use the standard molar enthalpies of formation for each compound to calculate the theoretical energy that would be produced from propane. So the delta H for this reaction is going to be the sum of the delta H F naught of our products minus the sum of our delta H F naught of our reactants. Plugging in these values, we have 3 moles of propane, which is negative 393.5 kilojoules per mole, plus 4 times water. And water in gaseous form is going to be different than water in liquid form. Gaseous is 241.8, and the liquid is 285. So you need to make sure you have the right state. And then we're going to subtract our products. So we have 1 times propanes, which I don't have memorized, negative 103.5. All these values can be found on your table of standard molar enthalpies of formation, or you can Google it to find the standard molar enthalpy of formation of any of these compounds at the state that they're in. Note, oxygen is in its natural elemental form, gaseous oxygen, so the standard molar enthalpy of formation of oxygen is just 0. Multiplying all these values together, you're going to get a final answer of negative 2043.9 kilojoules per mole. Okay, and because it's a molar enthalpy of formation and you're multiplying those N values, we need to take into consideration that this was for 1 mole of propane, and we don't necessarily have exactly 1 mole of propane being burnt. Looking back at the question, it started off by saying 2.45 grams of propane gas were burnt. You need to do a quick mole or a gram to mole calculation to get that your molar value of propane. So the molar mass of propane is 44 point approximately 1. So let's see the exact value, 44.0836 grams per mole, meaning we have exactly 0.055576 moles of propane. Multiply these two numbers together to get our energy that is being produced by the barbecue into just kilojoules, and your and just write it as energy produced is negative 2043.9 times 0.055576, which is negative 113.59 kilojoules. We now have the energy used and the energy produced. So we take those two values, and from there we're going to get our efficiency and write them out as a percentage. The percent efficiency is used over produced, which in this case is negative 9.0326 kilojoules divided by negative 113.59 kilojoules. This gives you a final value of 0.079519. Times that by 100% and round it to the proper significant figures, and you have that the final energy efficiency in this problem is 7.95%. That may seem low, but think about having a large barbecue and 1 chicken thigh on the barbecue. All the energy that you're being produced will not go directly into that chicken thigh. Every time you open the barbecue, heat is going to escape. So it's not a closed or isolated system. So this is, it's low, but it's not outlandishly low. This is practical number to get in one of these types of problems. The last thing I wanted to note is here both of the values were negative because we initially took our system, the heat from the system, and can use the law of conservation of energy to convert it into the surroundings, the Q equals negative delta H. You could have taken this value and brought it kind of into how much heat would be on the system side of things and had 2 positive values and got the same number. You just need to make sure that both of them are the same sign because you're not going to have a negative percentage for your energy efficiency. Thank you.